Here's my summary of what I'm going to talk about, or my criticisms of Atom Man Jimmy there. These are his fatal flaws in his arguments, okay? He argues that he learned physics by rote while standing on the shoulders of giants such as Rutherford, Bohr, Heisenberg, Born, and Chadwick. It turns out that these fellows, they were not giants. I think they were mental midgets, pygmies, dwarves. The conclusion of these mental midgets is the Copenhagen interpretation of QM. That's the one he concludes with. He says that's the one that's active today. That's the one people believe in the mathematical world. So that's the one you got to respect, okay, supposedly, or take on the basis of authority. The Copenhagen interpretation essentially states that you cannot even visualize the atom, so don't even try. See, people talk about the atom and what it looks like, and they draw a little ball going around the planetary model, the little ball going around the nucleus. No, don't even try to look at or to visualize it, because the Copenhagen interpretation says you cannot. You're an irrational individual if you try to visualize the atom. Okay, so please get that straight up front. If you thought otherwise, well, you got a problem. Okay, the only way to approach the atom is through mathematical description. That's the Copenhagen interpretation. That's what Jimmy's going to talk about. The mathematicians refer to this description as a theory. A description is not a theory, because a theory is an explanation. So there is no such theory as quantum mechanics, primarily because they don't have objects. Okay, they don't use objects, so whatever explanation they give you is irrational, and so I'm not sure it qualifies even as an explanation. I mean, if someone uses magic to explain something, has he really explained it? So there is no such thing as quantum theory. All there is quantum description. Description is not theory. Okay, quantum only describes. And the result, everyone simulates quantum mechanics with a planetary model, the atom, okay, and treats the atom as a solar system. Like with gravity, no one can justify why the electron or the Earth doesn't spontaneously fly away. That's the key issue in quantum mechanics and also in relativity. They cannot explain the force of pull. They cannot explain why the electron spontaneously doesn't fly away. That's the only question you got to ask any quantum guy. Any. Soon as he says, "Oh, quantum, and I study all these years, and I'm an expert," okay, say, tell me why the electron doesn't spontaneously fly away. What keeps it bound to the nucleus, to the proton? Same with the Earth in the case of relativity. They tell you that the Earth goes around the sun. Fine. Now you ask them, why doesn't the Earth fly out of the solar system spontaneously? And what are they going to say? That time is warped, and that's what prevents the Earth from flying out? You're going to say, well, time is a concept. How does time come in contact with the skin of the Earth? And a guy might tell you, it's just an analogy. You're not supposed to take it seriously. That's the answer they'll give you. They have no answer. So they don't have an explanation for why the Earth doesn't leave the solar system. They don't have an explanation, a mechanism for why the electron doesn't spontaneously leave the atom and fly out. Why do you have to spur it or stimulate it into leaving the atom and turn it into an ion, or maybe to conduct electricity? Why do you have to do something to it? Why doesn't it automatically, spontaneously, the electron, why doesn't it spontaneously leave the atom? That's the only question that quantum has to answer. And of course, they'll never answer that, because you can't do it with particles. It's the particle hypothesis, which is nonsense, which has to be debunked or thrown away, thrown in the garbage can once and for all. It's the particle hypothesis which we've been using for the last 10,000 years. Okay, here's Atom Man Jim Al-Khalili. He starts out more or less, saying that everything's made of atoms. Okay, he said, we asked where we had come from, how were the stars created, how all the elements were made, even how the universe itself had begun. And here he just tells the biggest fib that ever told. He says, one of mankind's greatest achievements is that we've answered these questions. Oh, you have? Oh, please answer why the electron doesn't spontaneously leave the atom. That's all you got to answer. And he can't answer that. So no, he hasn't answered all these questions. He's giving lip service. He's giving you a sales job here, okay? He's selling you something. He's giving you a false advertisement. The atom has helped us solve the greatest mysteries of existence. Has it? Okay, that's great. We don't know what an atom looks like, but he says it solves all of our problems. This is the story of the greatest scientific discovery ever. The discovery that everything is made of atoms. That's so strange that he would start his talk like that, because, here you have a fellow which he mentions, and that's Mr. Ludwig Boltzmann. And Ludwig, good old Ludwig, he came up with the idea that the atom is real. Okay, he in the 19th century, towards the end of the 19th century, he was arguing that there are for sure real atoms. No one in those days seemed to believe that the atoms were for real, because no one could see them or touch them. So they say, no, it's just a hypothesis. It's just something that we invoke. We say, oh, the atom, but there's no real thing called the atom. And it turns out that Boltzmann, I don't know, he's given credit for this by Jim Al-Khalili, but, Democritus already said that 2,000 years ago. He said, all that exists is atoms and empty space. I mean, how much more clear do you need it than that? So, no, Boltzmann was not the first to mention that, for sure. He says that Boltzmann committed suicide. He hung himself in 1906. Because no one would believe him. No one accepted his version that atoms were real. Okay, but here, good old Einstein, he came up in 1905, a year before Boltzmann's death, and he wrote 4 papers in 1905, annus mirabilis, so called, and in one of them, he explains Brownian motion. Guy in 1827, Mr. Brown, and he discovered that all these pollen were moving inside the water, and he said, why are they moving? They called it Brownian motion. And Einstein explained that in 1905, one of his 4 papers that he published that year. And he explained that, and he says, Al-Khalili speaks for Einstein. He says the pollen will only jiggle if they were being jostled by something else. Correct. I totally agree. We don't need Einstein for that. We don't need Boltzmann. We don't need Democritus for that. All we need is common sense. If something is moving, and physics is done with objects, first rule of physics, right? Then there had better be that something invisible, intangible, that is moving that pollen. They're bombarding it, and I talked about that in my last lecture. Okay, so you can see the movie that someone showed there. I essentially put it up, as an MP4, and you can see these particles. You don't see these particles, but you see that something's bombarding whatever's moving there, and those invisible, intangible thingies are thingies. They're particles of some kind. You can speculate whether they're round or cubic or whatever, but there's something there. You can't say there's nothing there simply because you can't see or touch it. And that's why we don't need Einstein to tell us, that pollen was being moved by particles called atoms or molecules. So Einstein said that water must be made of tiny atom-like particles which themselves are jiggling. Correct. And again, it just follows from the first law of physics, which is physics is done with objects. You can't do it with concepts. You can't do it with magic. Okay. Einstein proved that for Brownian motion to happen, atoms must exist. Now, he didn't prove it. There's no such thing as proof in science. All you do is you make an assumption. You say, you can say that there's something elongated, or there's a battering ram, or there are little particles. You can speculate on a lot of this stuff, but there better be something there. There better be something that's causing that. You can't say it's done with concepts, okay? The atom had to be real. Of course it had to be real. Now, if you want to call it an atom, which is what I call it, because this is what the word out there that's used, no problem. You want to call it X, but X had better be a physical object. That's the point, okay? And you can put it as the devil if you want, or God, or whatever, but it better be something. It better have shape, okay? Okay, so from there, what happened was they started looking at the atom, and here we have Rutherford. He tried to peer inside the atom. He ran his gold foil backscattering experiment, which is there more or less illustrated. It says Rutherford pictured the atom as a tiny solar system. Electrons, tiny particles of negative electricity, orbit around minute, positively charged objects called the nucleus. That's why 1 in 8,000 alpha particles bounce back. They're the ones that hit the tiny nucleus by chance. The rest went by without hitting anything. Rutherford's atom is almost entirely empty space. That's why nearly all the alpha particles raced through the gold atoms as if there's nothing there. There really is nothing there. Well, it's interesting that Al-Khalili would say all this after he says that nothing doesn't exist in quantum mechanics, that nothing is made of particles, which is what I talked about in my last lecture. I mean, he spent a whole hour telling you that nothing is made of something, and now here he says that atom is mostly nothing, which means an atom is mostly something, a bunch of particles. And what are those particles? Well, they're these particles that negative and positive, matter, antimatter, electrons and positrons, that they, and I like to explain it this is the way I like to describe this. I'm saying that you take a black ball and a white ball, you put them together and you create a no ball. And likewise, the no ball can reverse the process and turn it into a black ball and a white ball. That's essentially what these people are saying. They call it positive, negative, antimatter, matter, etc. Okay, what's the problem with that? In fact, Al-Khalili says if two particles, one antimatter, the other one matter, collide or meet, right? Oh man, it's the end of the universe because all that energy is released. And then this dummy, because there's no other word to describe him, he says that our space is constantly having all these particles, no particles, convert into white and black particles, which immediately recombine, right? What happens when you recombine matter and antimatter? Well, you have all this energy, all this big explosion. And here he's saying this is happening constantly in this nothingness that we call empty space. So all this jiggling that's going on there between matter and antimatter is supposedly every time two particles collide of matter and antimatter should release gazillions of energy, whatever that is. And it's happening in every little bit of space. It's constantly coming out and coming in, coming out and coming in. So we have all these explosions that should be destroying the entire universe. And they say these things, they don't even know what they're saying anymore. They just say whatever comes into their mind. And now they're saying that Rutherford says an atom is mostly empty space, which is what? A bunch of particles. So an atom is mostly a bunch of particles. Okay, now we got it. We got it straight. Important to keep it straight, right? Okay, but Ruthy had a little bit of problem, okay, because here he ran into this problem where it says almost immediately a problem surfaced. The electron should lose their energy, run out of steam, and spiral into the nucleus in less than a blink of an eye. Rutherford atom contradicted the known laws of science. Not surprisingly, all the established scientists of the day, including Einstein, were baffled. Scientific ideas they put their faith in all their lives had failed completely to explain the atom. The atom now required a new generation of scientists. Listen to this. It was crucial they had no loyalty or attachment to ideas held by the previous generations. Okay? So first, if you want to make progress, you got to stop listening to your teachers. That's essentially what these guys were saying. New generation came in, overthrew the old generation, and said, you guys are classical mechanics, we're doing quantum mechanics. And so he had to explain why the electron doesn't spiral into the nucleus. And that's when Niels Bohr comes around, okay, according to Al-Khalili, which is right. He's just reading history here, essentially, okay. And here's Niels Bohr, and he says, look, I'll tell you why. Because, what the electron does is quantum jump. Just goes back and forth between so-called energy levels, whatever that was, and that would explain in the spectrum of light, okay? And Bohr made it his mission to solve the problem of why the atom didn't collapse and why there was why there was so much empty space, which is what? A bunch of particles, right? As one of the new breed of theoretical physicists, he was prepared to abandon common sense and human intuition to find an explanation. Bohr's idea was to take Rutherford's solar system model of the atom and replace it with something that is impossible to imagine or visualize. Aha! So here we went into abstraction. We no longer had an atom. Now we had this abstraction, which was just an explanation. Says the not even an explanation. It's really a description, but he says it explained the behavior of light. Okay, that's essentially what he was trying to explain. So he explained that, but what he did, he gave an irrational description. The description was that this little bead just went back and forth between so-called energy levels for who knows what reason. So Bohr's idea was to take Rutherford's solar system model of the atom and replace it with something that is impossible to imagine or visualize. Of course, sensible ideas like empty space and particles moving around in orbits fade away and they're replaced with the nonsense called quantum jump. Why does that little bead go back and forth? That's what they got to explain, and of course they did not explain that. They just described and says it does so, that's it. In fact, Niels Bohr, there's one person who questioned, or at least one person, I don't know, questioned, and he said, yeah, maybe we don't understand it, but it happens. Okay, so what was Niels Bohr analogy for what was happening with the electron? He says he described the atom not as a solar system, but as a multi-story building. The ground floor is where the nucleus lives, with the electrons occupying the floors above. Mysterious laws, always mysterious, right, mean that the electrons can only live on the floors and never in between. And other mysterious laws mean that sometimes they can instantaneously jump from one floor to another. These are what we call quantum jumps. Okay, so what we have here is a notion of what quantum thinks is happening inside the atom. And again, it's all mysterious. Why? The reason it's mysterious is that they're trying to do it with particles. That's why it's mysterious. Once we abandon the particle, we've got it made. As long as you insist on the particle hypothesis, which is what quantum is all about, or waves, which is, again, particles, because what is waving? Particles. So you have two options. You can take the Newtonian version, which is, these particles essentially ran straight, and they were not the vibration of the ether, or you can take the Robert Hooke and Huygens version, which is the vibration of the ether, the particles of ether. But it's always been particles, or nothing. They have no other option. No other option has been put forth in the last 10,000 years until we now have the rope model. Pull. For the first time, we have all atoms are interconnected. That was never proposed, postulated by anyone. Okay, so that's new. That's what this site is about. Okay, so we continue here. Bohr went in there and says, when one physicist claimed that the jumps were nonsense, Bohr replied, yes, you're completely right, but that doesn't prove the jumps don't happen. Only that you cannot visualize them. So if you cannot visualize it, what kind of science is that? What kind of physics is that? Hopefully, if you're going to explain a mechanism, we can all visualize it. If you can't visualize the mechanism, then what kind of mechanism are you proposing? And this is where you can see that quantum got farther and farther away from physics into complete abstractions, irrationality, surrealism. Okay, because now for the first time, they no longer talk about what you can visualize. Okay, now they talk about complete mathematical nonsense, abstractions, and that's why to this day they tell you, oh, if you want to understand how what the atom looks like or what it's like or whatever, you got to take math. That's the answer. But not being able to visualize things seemed to go against the whole purpose of science. Correct. It does go against the purpose of science. Older scientists, in particular, felt that science was supposed to be about understanding the world. Correct. Not about making arbitrary rules that seem to fit the data. Boy, he said it perfectly there. Yeah, that's what science is. Science is about explaining rationally a mechanism. And if you say, I cannot visualize it, but here's the theory, you don't have a theory. What you have is magic. That's the issue, and that's what Bohr and Heisenberg and some of these other guys finally ended up with. They ended up with abstractions saying that's the world, that's the way the universe works at the subatomic world. Okay. Okay, so we have this fellow, Mr. Schrodinger. He comes in there and he says, "Oh, I can tell you what the atom looks like." He tried to have a picture still of the atom. He based it a little bit on what de Broglie suggested, which is that you have integral waves. The electron has integral waves around the nucleus. And Schrodinger came up with a similar idea. He just came up with his equation. He said the electron, essentially this is his interpretation, the electron is in fact a wave of energy, whatever that is. There's no such thing as a wave, there's no such thing as energy, so we still have abstraction. What are we staring at? We don't know. Vibrating so fast it looks like a cloud. So all we have is a bunch of abstractions. Again, we don't have no real atom there. We have wave of what? Of energy. What is energy? Oh, we don't know. We're still trying to figure out. We're still trying to define it. A cloud-like wave of pure energy. So what have we learned? What is an atom? Just energy is a concept. Wave is a concept. So we have the waving of a concept. That's what an atom is. So he had a problem defending his vision against people like Heisenberg. And Heisenberg essentially tore him and Einstein to pieces. Okay, why? Because Schrodinger couldn't keep up with him. Now here's Schrodinger again, okay? And what he couldn't explain especially was the, he had a picture, but he couldn't explain the nagging problem, which was the strange instantaneous quantum jumps. His cloud model or his vibrating wave model of energy, he said, well, why does it fall to a lower energy level and rise to a higher energy level? And he couldn't explain that with his equation, with his vision of the atom. Okay, so this is where quantum was at a crisis. And who came to save the day? Well, good old Wernicke. Okay, Wernicke, Heisenberg, he came up there and he says, oh, I can tell you why. He had this notion. He said he believed it was time to give up a picture of the atom at all, completely. We can't picture the atom. Okay? All human attempts to visualize the atom, to model it with familiar images, would always fail. He decided to abandon all pictures of it and describe it using pure mathematics alone. The atom didn't just defy visualization. It even defied traditional mathematics. He came up with these quantum matrix, and he says, this is what the atom looks like. Pure math. So if you want to know exactly what an atom looks like, they're going to tell you to take a course at the university level, because otherwise you won't understand what it looks like. It's like saying, what does a rock look like? Oh, you got to take a course at the university level to know what a rock looks like. Okay, so you go to the university and you say, okay, I want to find out what an atom looks like. This is what an atom looks like. There you have it. It's a little matrix, bunch of equations, a couple square roots, right? Cube roots, maybe. You have the irrational number there. So now you know what an atom looks like when you go to the university. Okay, you got to go to the university to find out that it looks like that. That's what you spend 10 years at the university for. Yeah, they have no picture of the atom, and to make things worse, good old Wernicke came up with a new idea which just shocked the pants out of everybody, and that was his notion of the uncertainty principle. He says, I know why the atom cannot be visualized. It cannot be visualized because it's inherently unknowable. Okay. And so good old Al-Khalili, he explains, he says, there is a fundamental limit about how much we can know about the subatomic world. That's what Heise found out about. If we know where an electron is at a particular point in time, then we cannot know how fast it is moving. But if we knew its speed, we would know its position. That's essentially Heisenberg's uncertainty principle, or principle of indeterminacy. Okay, it's a fundamental truth about how nature behaves at the subatomic scale, known as Heisenberg's uncertainty principle. No, it's how nature behaves when you model it with particles, which is irrationally. Okay. The reason this is nonsense is because, and you can try this experiment at home, always in the presence of a trained quantum mechanic. Okay. You put a ball on your table. Do it carefully, okay? This is a very dangerous, very expensive experiment, okay? You put a ball on the table and you watch it for a while and you'll notice that it doesn't move. So you know its position. You know how far it is from the edge of the table, all that. You can even measure and check, and it's always there. So you know its position, but you don't know its speed because it's not moving. Now roll it across the table. Well, now you know that it moves. You can even time it. You know, you can check how fast it's moving. What is its position? Position, location, really, in rational science, location is a static concept, whereas motion, or momentum as they call it, is a dynamic concept. So, yeah, the more you know about how a ball moves, the less you know about its location. The more you know about its location, you know nothing about its motion. That's what Heisenberg discovered. He got a Nobel Prize for that idiocy. Okay, and today it's one of the golden rules of quantum mechanics. So please don't laugh at it. Okay. Here's good old Jimmy gawking at duality. You know, the fact that everything in quantum mechanics is a paradox, among them complementarity, invented by Mr. Niels Bohr, saying that the light is both a particle and a wave. And that goes for everything, essentially, for the electron, I guess the atom, everything behaves as both, a particle and a wave. That way they cover all the bases. It never occurred to them that it could be neither, that maybe it's a rope, light. That's a totally different concept completely, okay? A totally different theory. Atoms are not just unimaginable, they're self-contradictory. I mean, these people are admitting it. They're telling you in your face they're unimaginable, self-contradictory. And then you have all these people out there who are, you know, they just look at these things very superficially and they say, oh no, they have proven the atom. We wouldn't have computers if it weren't for quantum, blah, 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 blah. Here they're telling you, atoms are not just unimaginable, they're self-contradictory. They behave both like particles and waves. Yeah, no kidding. And it gets weirder. Oh, it does, okay. When you aren't looking at an atom, you're going to need a couple drinks to understand this, okay? So go get your beer, okay? It behaves like a spread out wave. But when you look and to see where it is, it behaves like a particle. This is insane. Yeah, completely. Totally agree. So he did have some good points in his presentation. He said it's insane, it's surrealistic, it's poppycock. That's what he's saying. First, atoms couldn't be visualized at all. Now it seems they changed completely in character depending on whether or not you're looking at them. Now, how sick is that? And this supposedly is what all these mathematicians believe in. Okay, so Jimmy continues with his presentation on the atom. He says, look, good old atom man there, okay? And he gawks. He says, it revealed a shocking contradiction at the heart of nature. Everything we see is made of atoms, and yet atoms themselves are unknowable. They can only be understood through mathematics. So if you want to know what a dog looks like, you got to take a course at the university level because you can't just point and know what a dog looks like. You need to find out, the wave equation of the dog or something, I don't know. The probability wave of a dog to know what a dog is. That's what these people are saying. Okay, and so he continues, he says, the old God was replaced by the new. No kidding. I mean, I preferred the old God, really. The guy with the magic wand, I could understand that. I could see that God, who is it? Michelangelo, he painted God, so I respect him because now I know what God looks like. He's got a beard, a little magic wand. He's got all these saints and angels around him. The old God was replaced by the new, no doubt. Chance and probability became interwoven into the fabric of nature itself. And we could no longer describe atoms in terms of simple pictures, but only using pure abstract mathematics. Now, how's that for physics? How's that for understanding how the universe works? You got to take a course in mathematics just to know what an atom looks like, because all you can do is put an equation, in this case the matrix that Wernicke invented, okay, and so here we have good old Niels Bohr, and he summarizes for us: everything we call real is made up of things which themselves cannot be regarded as real. Of course, he never defined the word real. He didn't know what the word exist means, because he didn't define that as well. But he talks about what is real and what is not real. But that's his conclusion. It just gives you an idea. These people have no clue about quantum, which is how they pretend to describe the atom. And they can't describe it except mathematically. And I mean, they can't point to it. They can't give you a picture, a drawing of the atom. But they say that an atom is what caused the pollen, Brownian motion, would cause the Brownian motion to occur, to the pollen to move. They say it's got to be something, but now they have that something, and they say, well, but you cannot even visualize it. You're not allowed to. You can only approach it through mathematics. Solvay, 1927. This is another gawking moment of good old Al-Khalili. He says, Solvay, 1927 that's when the conference took place in Belgium, was the turning point at which the rest of science establishment came to embrace the Copenhagen interpretation, and that interpretation is still accepted today. That means today the Copenhagen interpretation of quantum mechanics is the authoritative one. It's the party line, okay? And what do they say? You cannot visualize, you cannot even imagine the atom. Don't try. If you do, we're going to call you a heretic. We're going to say you're a crank, a crackpot. So don't even try. If you draw the atom, you're going to be kicked out of quantum mechanics. You're not supposed to draw it. You're supposed to express it in matrix form. Okay? You got to put all those square roots, numbers, then you're okay. But don't try under no circumstances to draw and illustrate the atom, because it's you cannot even visualize it. Whatever you draw is wrong. That's the Copenhagen interpretation. Okay, all the physicists that I use, all the physics that I use, this is Al-Khalili giving us his testimony. Okay, all the physics that I use in my research, certainly the quantum mechanics that I teach my students. This is how these things get rolled by from generation to generation. Okay, passed on down. And that fills the textbooks on my shelves is based on ideas that were hammered out and crystallized here at the Solvay conference in October 1927. In a sense, everything I know about the way the world around me is made up started here. Over the last 80 years, it has been proven right time after time, and its authority has never been in doubt. Now, how's that for a statement of religion? Is quantum mechanics a religion or what? I mean, these people just learn it by rote. They repeat it because it was handed down by the great white fathers of quantum mechanics. They're not willing to challenge it, partly because they would be kicked out of quantum mechanics, meaning they will not get a job, a career. So they have to fall in line. Those people who are smart and they say, well, I can't take this any longer, they drop out and become engineers, lawyers, doctors, whatever. But those who stay, they have to repeat the catechism. They have to know it by heart. And that's where good old Jimmy falls in. That's why I have little respect for him. All he did was memorize what the forefathers told him, and that's it. He just repeats it now on TV. That's all it is. Okay. Couple more things here. Here's, they say you can't picture the atom, you can't picture the electron. Here's a Swedish team, and they took pictures of the electron. And they made this movie by taking snapshots, many snapshots, and they explain how they did it. You can look it up. But this is their result. They say that's what an electron looks like, a little ball that goes around the atom. Okay? And so on the one hand, you have the quantum guys saying, You cannot even imagine the atom, let alone the electron. These people are saying, oh, we filmed it. So now, what are we supposed to think? I mean, are these guys idiots or what? All of them. Because they don't even know what the other guy is saying. We don't even know what the catechism is anymore. I mean, are we supposed to imagine, visualize the atom? Or are we not? These people are saying we filmed it. These other people say, no, you can only get it through a little matrix, a little mathematics there. What are we supposed to believe now? What are you supposed to, what is quantum mechanics? What is the theory? Okay. Okay, so what is that these people missed all these years? Well, here you have the rope model, okay? Two-dimensional, three-dimensional rope model of the atom, very simple. And so yes, we can visualize. We had better visualize it if it's a physical object, okay? And are we supposed to visualize or imagine or watch the quantum jumping? Here it is. Here's the quantum jumping in 2D, but you can understand what's happening there. The atom expands and contracts. By doing so, it torques the rope. That's it. That's quantum jump. That's how difficult it was all these years. All we had to do was make a new assumption about, you know, the atom and how it really works. Okay, so getting here the final part. One more time, I'll go through the conclusions. My conclusions, in other words, the fatal flaws I want to point out in Al-Khalili's argument. First, he argues that he learned physics by rote. Okay, essentially that's what he's saying. He just gawks at the forefathers that he had that gave him all this information. He calls them giants, but he's Atom Man, so I guess if he stood on the shoulders of these giants, you know, they were maybe pygmies. I don't know, dwarves. The conclusion of these mental midgets is that the Copenhagen interpretation of QM, which says, essentially states that you cannot even visualize the atom, so don't even try. Okay, even though here you have these people in Sweden that they filmed the atom, so they do a little more than just visualize, they filmed it. Okay, they claim that they filmed it, and you'll find a lot of people who say they took pictures of the atom as well. Okay, so I don't know what all these people are talking about. And the only way to approach it through mathematical description. The mathematicians refer to this description as a theory. It's not a theory because a theory is an explanation. Quantum can only describe, okay? So there is no such thing as quantum theory. And the result is that everyone anyways just uses the planetary model to do, you know, electricity and ionization and collisions. They use that model anyways. So by default, that is the quantum atom, except that they'll always deny it at the end of their presentations. And just like with gravity, you know, they cannot explain why the electron bead does not leave this solar system planetary model. Okay, so there you have it in a nutshell. What should you think about Al-Khalili? Well, not much about him. He didn't make a very good case. He started saying that they explained everything. It turns out they explained nothing. They don't have any explanation, any rational explanations, which means they do not have an explanation. For that matter, I can just go with the explanation we had 1,000 years ago. You know, angels move the earth around the sun. That's a good explanation. Why not? I mean, better than this one. At least I can visualize angels going around the sun, pushing the earth. Okay, I can also visualize angels on two magnets holding hands and attracting each other. You know, I can do better than quantum just by postulating angels. So maybe my angel theory is a little superior to quantum mechanics, because this one they tell you can't visualize it, don't try to imagine it, because you can't. The only way to approach it is go to the university, learn a bunch of math, and then you'll understand. You know what I mean? Anyways, with that, I'm going to see you on Wednesday, and I'm going to continue with Al-Khalili, because he's got a lot of material out there, and it needs to be debunked. It needs to be brought to light what these guys are passing on down, not only to his students, to people that he teaches directly, but also to the new generations who, you know, just come in and they want to get some information on quantum mechanics and general relativity, and they come in and they just get bits and pieces. Oh, okay, so that's what we've discovered, huh? So we need to, for those few people who stay a little longer and they are really critical, they will find that there's a lot to criticize in mathematical physics. None of it survives. None of it survives.